So this is a really good example problem because it also includes some orbit stuff, which we're having a test over as well, so it's a good review. So in March 1999, the Mars Global Surveyor entered its first orbit about Mars, sending data back to Earth. Assume a circular orbit with a period of, gives it in minutes, you don't need it in minutes, 7.08 times 10 to the third seconds, and an orbital speed of 3.4 times 10 to the third meters per second. And it gives you the mass of the satellite, which is 930 kilograms, and it gives you the radius of Mars, which is 3.43 times 10 to the 6th meters. So the first one says calculate the radius of the orbit. This is a classic one. For some reason, it's very tricky on tests. So you're given period and you're given velocity. So you can just use velocity equals 2 pi r over t. I see a lot of people wanting to use like Kepler's third law to solve this. And so you're finding the radius of the orbit, so you just isolate for r. So you do r equals v times t over 2 pi, and then you can solve for the radius of the orbit. Then it says calculate the mass of Mars. For that one, you are going to think about your force diagram. So you have your satellite orbiting Mars. Your force is just the force of gravity. So the net force equals force of gravity. Net force is mv squared over r. Force of gravity is gmm over r squared. Little masses cancel. One of the r's cancels. And you're solving for the mass of Mars. So you isolate m. So we get v squared times r over g. And that will give you the mass of Mars. Then it says calculate the total mechanical energy of the GS in its orbit. So here's our energy question. Our total mechanical energy is going to be K plus gravitational potential energy. And anytime you have gravitational potential energy of an orbit, you're going to be using the equation, can't talk in very different things. So you have K equals 1/2 mv squared, and then your gravitational potential energy is Gmm over r, and it's negative. So from here, that's just the total energy. So you know all of these things, and you're just plugging in the numbers. What mass is this little mass? It's the mass of the satellite, yep. And then this mass is the mass of Mars. How about the r? Is that the radius of Mars or the radius of the orbit? It's the radius of the orbit, because that's where it is, that's how far it is from the planet. And then part D says if the satellite was placed in a lower orbit, closer to the surface of Mars, would the new orbital period of the satellite be greater than, less than, or equal to the given period? And so for that one, yes, it's going to be less than. Now you have to support you have to justify your answer. So to do that, I've had a lot of people answer a question like this and try to justify it with this equation, saying that if radius goes down, period will go down. But that's assuming that velocity is constant. The velocity is not going to be constant when the radius goes down, because now the satellite is closer to the planet, so it has to move faster to avoid being sucked in. So what you need to do is use Kepler's third law. So period squared, actually, you're doing period squared over radius cubed equals 4 pi squared over gm. So then you would use this to show that if radius goes down, period goes down as well. And then you have to, anytime you use an equation justify your answer, you have to address every other term in the equation. So G is a constant and mass of Mars is a constant. So those are all constants there. So if R goes down, period